Hello, I'm Stefan Graeber, for lxd, and today we're going to be talking about storage. This is going to be the first in a number of videos around storage topics, thanks to our documentation having been recently updated and including a lot more help around storage, different variety of storage topics. Now, in this video, what I want to do is just kind of go over the list of storage drivers that lxd supports, and then look at how you can try them for yourself, and also how to do a very quick benchmark of lxd through a built-in tool that ships with the lxd snap. lxd supports, well, as it currently stands, 6 storage drivers. We usually can count it as 5 because 2 of them are Ceph. The first one is the directory driver, which just takes a plain old directory and just dumps files on there. It's the simplest, but it's also quite often the slowest or the least featureful. Then we've got btrfs, which is a lot more featureful. LVM, that's mostly useful for those who already use LVM for other reasons. ZFS, which tends to be our kind of recommendation, and then we've got Ceph and CephFS for distributed storage. There's no real one magic bullet, take this particular storage driver and you'll be good. We tend to recommend ZFS, but that's not always available. It's not in the mainline kernel, and it's also not perfect. For example, if you want to store Docker containers, you're probably going to be better served with btrfs. Obviously, if your own system is already stored on btrfs, then go with that. If your system is already using LVM, you might want to use that instead. If you really need to just do a few tests and you don't want to pre-allocate any storage or anything, then directory might be for you. Now, I mentioned looking at performance, and that's something we've been doing for a number of years actually, where we've got daily tests running on Jenkins using a benchmarking tool that we wrote that then tries to create a container, create a batch of containers, stop one container, stop a batch of containers, delete containers, and does that every day on every single one of the storage drivers, and that gets us some interesting metrics. So if something gets slower, if we break something, we'll eventually notice it in there. And that same tool is something you can use yourself. So we move over here to a terminal. I'm running lxd 5.3, and there's a command called lxd.benchmark that comes with the snap. If you're not using the snap, your distribution might have packages as lxd-benchmark, so I would look for that. Otherwise, you might need to build it from source. Now, that tool supports the same actions as we saw earlier in the graph. So simple creation plus launch, plus start, starting containers, stopping containers, deleting containers. It can run batches of different size batches. You can run it in parallel or not, and it supports getting its output in CSV format if you want to do some kind of graphing, which is exactly what we do. Now, prior to using that tool, you're going to want to copy some images locally. You don't want the download time to be counted in the benchmark run. So in this case, I'm going to be copying a basic Alpine image and a basic Ubuntu image. There we go. And as it stands, I'm configured with one storage driver, which is a directory driver, so kind of the most basic setup. And we can start with, say, create 100 Alpine containers and see how that goes. Again, this is a very, very fast system. It can run on 12 cores. That's why we see a batch size of 12. And it's on very fast NVMe storage with a lot of memory. So this is going to be the best case scenario. Also, Alpine is very, very small, which helps a lot in this case because the unpack time doesn't really impact the launch time. Now, we delete that batch. There we go. And let's create Ubuntu. This should be significantly slower because Ubuntu is significantly larger. This is also going to use a lot more CPU. So if you look at another terminal, you can see that this poor machine is now melting because every single instance needs to unpack the entire image over and over again, which is going to be slow. And as we can see, this is going to be slow. It's going to take quite a few seconds to actually unpack. That's one of the main benefits from using something like ZFS, like btrfs, or even LVM, because those can use copy on write. They will unpack the image once and then will just clone without actually copying any data for any subsequent creation. Like we can see, the system is now reaching a load average of, well, it reached a load average of over 70. It's coming down a bit now, but it's very, very loaded. And we're still not done. We crossed 48 a few seconds ago, so there's still more to be created, as can be seen here. We just started another batch. So it's okay for something tiny like Alpine, but if that's all you're gonna be kind of testing with, that might not be the whole picture. So just waiting for that batch to complete. I also want to just remind myself of how long it took. All right, so it took 7 seconds for 100 Alpine. It's gonna take well over a minute, possibly a bit over 2 minutes, I'm guessing, to create those Ubuntu containers. Okay. On the upside, deletion should be pretty fast because, yeah, that on NVMe should be rather quick. The main issue really here is the fact that we need to unpack and recreate the same files over and over again. Come on. It's taking a bit longer than I expected. And we're getting close to the last batch now. Not quite. Okay, another batch is starting. Poor disk. The other thing is that this is using a lot of space. So if we actually go look at the storage pool, creating 100 Ubuntu containers is currently written almost 40 gigs. That's very, very significant. And is another reason why you definitely want to use something that can do copy and write whenever possible, because that's gonna save you from that cost as well. Okay, how many do we actually have? Just listing the name and everything else. CSV. Wondering how close we are to that 100. 96. Okay, we're getting there, It's probably finishing the 96, that's why it didn't actually report it yet as progress. It's just a few more seconds, but that's gonna have been very, very slow. It would have taken, I don't know, 3 minutes, 4 minutes, something like that. It's pretty slow, but a great example of why copy and write is a good idea. And we're done. Okay, batch processing took, yeah, that's 3 minutes-ish, 4 minutes. So that was pretty slow. How much space did it use in the end? It used a total of 47 gigs. Okay. All right, so let's delete that and just remember 216 seconds for 100 Ubuntu containers versus 7.3 seconds for Alpine. Just gonna use another terminal down here to just write that down. So directory was 7.3 for Alpine and 216.2 for Ubuntu. Thankfully, deleting stuff is quite a bit faster. And we're done. Okay. No more disk space usage. All right, well, let's try ZFS. It is a very, as I said, like very well-rounded file system, but it's also, so in this case, like ZFS and btrfs that we'll try afterwards, they're not in their base scenario because they are effectively using a loop file on top of the ext4 file system that's used for the directory backend. You should try and use a dedicated drive or partition if you can for additional performance, but that should still be significantly better. I'm just gonna be setting it as the default storage pool. And before we do a full batch of 100, let's actually just do a single Alpine and a single Ubuntu. And there's a, oops, need to delete in between. There's a good reason for that. ZFS and btrfs both take longer for their first instance because they need to do the unpack for that one. Afterwards, creation is significantly faster. So if we do, let's do 100 again, and let's do Alpine first. So number 2-bit is 7.3 seconds. Which, I'm gonna get close. 7.7, okay, so it didn't beat. As I said, like, ZFS does have a reasonably heavy cost per instance creation because we need to run a number of commands to actually set everything up because it's very featureful, which means lots to configure. Anyway, let's delete that batch. And now for the more interesting one, let's do it again with Ubuntu. That's where we should see things being a bit different. Right, we're already halfway through. And doing, there we go. So we can see that for ZFS, whether you're creating Alpine or Ubuntu instances makes no difference, which is exactly what we should be seeing with a copy on write file system. Because whether it's like it's just creating deltas and how big the source of the delta is doesn't actually impact the creation time. And that's what we are seeing here. We can create 100 Ubuntu instances in exactly the same time as it took to create 100 Alpine instances. And that definitely wasn't true when we were creating Alpine containers earlier. Also, the disk usage, I didn't show it here, but it would have been effectively 300 megs, the size of a single instance. And no matter how many you create from that, that wouldn't increase until those instances do something. That's the whole point of copy on write. All right, next let's create btrfs. Btrfs is a bit simpler than ZFS in the way we drive it from lxd, so we'd actually expect that to behave even better. But let's see. So let's start. So we need to do the same trick. So we'll first do a single Alpine, delete everything, single Ubuntu, delete everything. And then we can go ahead and do 100 Alpine. Okay, 3.2 seconds. So this one ended up definitely beating both ZFS and even directory, which is what we like to see. And now let's try to do the same thing with Ubuntu. Right, and Ubuntu took 5.14 seconds, so significantly faster than directory, even faster than ZFS. And yeah, that's really showing kind of the performance you can expect from copy on write. I believe I actually have an NVMe partition I can use. So let's see if we can do another run on, well, I don't know, let's do, I guess we could do btrfs again. Well, or maybe ZFS, because ZFS was slightly slower, which should make any difference more visible. So we're gonna delete the ZFS pool and create it again, but this time we're gonna be using a dedicated partition. I think P3, there we go. So then instead of being through a loop device, it's going straight to a dedicated partition on the NVMe drive, which might actually improve its performance a tiny bit. So again, I'm gonna need to do init 1 for Ubuntu, delete everything, init 1 Alpine, and delete everything. And then let's do batch of 100 Alpine. So I'm just gonna log that as ZFS on partition. And let's see. So it did it, that was actually slower, wasn't it? Yeah, that's interesting. Don't know why that is. Let's see if a second does the same thing. Looks like it will. Huh. So I was actually expecting the direct partition to be faster because normally it should be. But in this case it is slower, so that's puzzling. All right, not much point running the other test because it's also going to be slower. But that's kind of the whole point of this tool, is you get to play with different storage configurations. Can also reconfigure like in more details exactly how you set up, whether it's ZFS, btrfs, or LVM, and then run those kind of loops to see what's going on, how fast lxd is. And also you should definitely run something like I was doing earlier with htop to get an idea of, are you just waiting on storage, or are you like using all your CPU unpacking things? That's also pretty important. And you can also use it to run. So if we switch back to, I guess, btrfs, and instead of doing init, we do launch on Alpine, and we want 500 of them. So in this case, it's not gonna only create them and also start them at the same time, which then stresses both storage and CPU, because as they get created, they will also need to start, which is then gonna use a lot of CPU and create a lot of processes and make your system very, very busy. So that's gonna be significantly slower than the time we were looking at earlier. As a reminder, we were doing everything in 5.14 seconds for just the creation. But for launch, that's gonna take a fair bit more time. But that also lets you really kind of stress your system. It's also interesting to see whether the speed slows down significantly or just a tiny bit. The slowing rate we're seeing here is kind of what I would expect because of the added load that gets added as more and more instances get created. And yeah, we can see like it creates them pretty quick, but then they need to actually start, they need to spawn in it, they need to get an IP address and do that over and over and over again. And that's using quite a lot of CPU. I'm just guessing the system is not that busy actually. 7.9 is not bad. But yeah, it's currently at 192 containers already. Let's see if we can have lxd list them reasonably quickly. Yeah, it's not bad. So one thing that's worth mentioning there is if you're gonna go down that route and like create a lot of containers, you need to keep in mind that there are some things you might want to configure on your system. We've got a documentation page called production setup, which has some steps you should be taking if you're going to be running more than 100, 150 or so containers that are running systemd. In this case, I'm using Alpine, which doesn't run systemd, so they shouldn't be impacted by that. The limit that they're most likely to gonna be hitting first is if you exceed 4,000 of them, 4,096 to be precise. The Linux bridge, lxd.benchmark, is going to be saturated and will not let new instances get connected. To get past that one, you've got two options. One is create a different bridge and use that for the second batch of instance, or switch to Open vSwitch, which doesn't have the particular limit. Never, like, regardless, we're going to have a bit of an issue, which we're actually going to be seeing here, which is the default bridge is configured with a /24 subnet, which means 253-ish, 254, I guess, usable IPs. We're running more instances than that, so there's not going to be enough IP addresses to go around. So only the first 250 or so will get IP addresses, and the rest won't. IPv6 won't be impacted, but IPv4 will. And if you want to avoid that and actually give connectivity to all of the instances, you will need to reconfigure your network to use a larger subnet. Okay, 192 was the last snapshot we saw, but they're still quite actively getting created. You can also use lxc monitor to see what's going on at the lxd API level. You can see it's busy. And another thing you can do, there's an argument for that to the command line, is actually control the size of the batch. By default, it picks the number of CPU cores. So in this case, it's going with 12. But if you want to try, okay, see what happens if you only have, say, 4 API clients that are really throwing stuff at lxd very, very fast, then you can reduce the size to just 4. And then you're going to be creating the same number of instances, but with just 4 clients running against lxd. Just want to see how many we actually have at this point. I suspect we're getting very, very close. 384. Okay, so yeah, that's... Oh, I just reported the 384 actually. And we can see the speed has been slowing down significantly, thanks to all of those instances actually doing stuff. And also the kernel getting busier and busier. Like on the properly tweaked system, so following all of those guidelines from the production setup, and with probably more memory and better storage than I've got here, we've been able to run way past 1,000 instances, usually past the 4,000 mark, and up into 10,000 or so instances on a single system. One thing to keep in mind there is that those instances do nothing. Obviously, as soon as they start to really like hit the CPU and do stuff, most servers will melt, because that's a lot of systems to be running. But that's kind of the beauty of containers, that if they're just a bunch of processes, if those processes are doing nothing, then your system is not really loaded, which is what we're seeing here. Like the system is getting slow because we need to acquire locks in the kernel and everything. That's kind of slowing down with all of those instances working. But the actual load on the system is not bad. Like a load of 7 on a system with 12 cores is perfectly acceptable. The system is still snappy, it's not overloaded or anything, despite what it's going through right now. Actually, what I described earlier, we can see it now. We can see that all of those Alpine instances are just getting stuck running the DHCP client. They're not able to get an IP. All right, what's our count? Might reach 500, might wrap up slightly earlier than that. Let's see. Oh, we hit the timeout on one of them. So yeah, the system is slowing down. 440. Okay, so we're getting very, very close. Yeah, they're not having the best of time right now, those poor instances. Also want to check the rest of the resources. Yeah, so memory is still pretty low. They're only using 8 gigs, but I guess the bulk of that is not even the instances really. Looks like lxd might be using a few hundred megs of RAM here, and the host system is using a bunch too. The other thing we're seeing here is like some of the side effects of running extremely large batches of instances at the same time is the host system reacts to each instance starting up, and that's causing udev and other daemons to start up. That's what we kind of see in the kernel log, with all of the network devices being added to ports, network devices getting renamed. This is triggering a bunch of events that the host system reacts to, and that can also slow down and explain some of that kind of curve you're saying, where the more instances we've spawned already, the slower it gets to create additional instances. One thing that can be interesting is that once they're all started and they're all done booting up, then you can start a new batch, and you'll probably notice that one will start just as fast, because there's nothing else going on with the background ones. Okay, let's see what's going on now. Oh, we get a new batch. Looks like we did. Are we at the 500 mark yet? At 440 last time. Oh, another instance failed. Come on. 481. Getting there. Another couple batches and we'll have a 500. Well, minus two of them, as the log was showing, failed to start. Either failed to start or failed to create, I don't know. We'll see. Oh, looks like it's starting to really struggle. I'm not sure if we hit another limit that would normally be bumped. I don't think we should. I think the lower limits are mostly inotify related and so mostly impact systemd. But I've not done this in a little while, so I might be misremembering. We're getting another batch. Okay, so that might actually be the last batch. Given each batch is supposed to be 12, and we've seen 2 batches go through. 495, okay. There we go. Completed. 528 seconds for 500 that were both created and started on the system. So I actually want the status stopped. Let's see how quickly it can give us that. I'm wondering those 5 instances, if they fail to create or if they fail to start. So that should tell us. Again, that particular query is not super cheap because lxd actually needs to go and check the status of every single instance on the system, and they're a bit busy. Let's look at the load. That should be calming down now. Yep. It's going down significantly. Okay, no instance stopped. So that means that the instance failed to get created, did not fail to start. Okay. That can happen, especially since lxd was effectively being hammered with exactly batches of 12 requests exactly at the same time, while past instances were still starting up and talking to lxd. That's not impossible. And that's another thing you can kind of look on your system, see if the elevated load starts creating errors. And if it does, kind of what batch size can you actually handle? You could have used that. I can do it on delete. There's an option here for number of parallel threads, which defaults to the number of CPU cores. So in this case, 12. So that would be your case of like 12 API clients talking to lxd at the exact same time. Now you might want to play with that to get an idea, a feel for like how many concurrent requests can your server actually take on, and so do some of those loops with -p4, -p8, etc. to see what's going on. So say we want to clean it up with actually we can try and clean it up by making it burn. Let's see. Let's do 32 parallel threads that want to tear everything down. Let's see what happens. Not gonna be running that one to completion, I don't think, but because it might take a little while to actually shut everything down. Trying to get to the API just to see what's going on. But that's something you can do to get an idea of just how quick you can create or get rid of all of that. So in any case, this was a quick look at the lxd benchmark tool and some of our different storage drivers. So in this case, we looked at directory, btrfs, and ZFS. I could have showed LVM too. You can create it the exact same way. It just tends to be slower than the other two by quite a bit. It is still going to be faster than directory, I would expect, when creating large batches of Ubuntu instances. But overall, it's going to be significantly slower than both ZFS and btrfs. So hopefully that's a good quick intro to our different storage drivers and how you can play with them and maybe do some benchmarks for yourself to see what works best for you. And yeah, the next few videos are likely going to be around some other storage topics, maybe doing a deep dive into some of the specific storage drivers and how to set them up and how they work. Hope you enjoyed this video. If you've got any question around this or anything else, you can leave them down in the comment section below or on our community forum. And I'll see you in the next video. Thanks for watching. Bye.